Hi, Honors Chem class. This is Mr. Kotz. Um, Obviously, you see that I'm not in the building right now. This morning, when I was setting up an AP Biology lab, I was putting a thermometer into a rubber stopper, something that I've expressed 100 times during my safety discussion at the beginning of the year as something that's very dangerous. And I found that out firsthand today, and the thermometer snapped in my hand and basically dug down a pretty good way. So I had to go to the urgent care, get some stitches, and am out of the building today. I have pictures that I'll show you if you want to see them. It's pretty crazy. But anyway, I do want to put together a lesson for you and begin chapter 12, which is obviously the next thing in our discussion. You did take the test on Friday, or the quiz on Friday for chapter 11. Have not had a chance to grade those yet, but we'll grade them probably this evening and get those grades in, and we'll be able to talk about that tomorrow. So with that, let's begin our discussion on types of mixtures. These are things you should be relatively familiar with already at this point, but it's good to go over things and kind of talk more scientifically as to what we're seeing when we see different types of mixtures. So with that, solutions. A solution is basically a mixture of usually a liquid that dissolves some sort of solid. That's a solution. The pure liquid itself is not considered to be a solution. It has to have something dissolved in it. Something that is soluble can be dissolved. If we look at solutions themselves, there's always a solute and a solvent. The solute, I refer to that as kind of the little guy, the small one, like salt crystals or sugar crystals or something like that. The solute is the little thing that's being dissolved, and the solvent is the thing that is doing the dissolving. The little, I don't know, phrase that I remember, the solute salutes the solvent. Solute salutes the solvent. Basically, the little guy has to salute superiors. I guess, in my mind, the little guy, again, being the little crystals, the big guy being the solution there, the liquid that it's being dissolved into. So if that helps you with your remembering all of those things, that's good. A solution is a homogeneous mixture of two or more substances in a single phase. So the single phase, essentially what we're dealing with, it all has to be held within the liquid state. If we take a look at on the left-hand side here, oopsie daisy, I gotta get my pointer. On the left-hand side, we have a solution. We don't see any distinguishing different compounds in there. We see just liquid. So whatever's dissolved in there is presently in the liquid state. You can't see it with your eyes. It's homogeneous mixture. This over here would not be a homogeneous mixture, nor would it be considered a solution because you still have solid and liquid. Technically speaking, it's not a solution. If you were to put this through a centrifuge and isolate all the solids and pour off the liquid, that liquid would probably have some of the solid dissolved into it, and that liquid would be a solution. But if it has solid in it still, it's not considered to be a solution. All right. Components, we had talked about this. The medium that does the dissolving is the solvent, so that's the big guy. The big guy being the liquid that everything is being poured into. So solvent is the big guy, solute is the little guy. Again, solute salutes the solvent. So in this case, our solute would be the sugar that we're putting in, and the water is the solvent. Easy enough, no problem. Suspensions. Aside from what happens when you misbehave in school, suspensions are a mixture of large particles that don't dissolve into the solution, or they'll settle out. So if particles settle out, unless they're continuously agitated, is considered to be a suspension. If you take salad dressing, Italian salad dressing, for example, up here you see the oil, and down here you see large particles. Unless you continue to shake your zesty Italian dressing, it's going to fall out of solution. And when you see that, if it just sits there, if you see it fall out of the solution and create two separate things, that's considered to be a suspension. And again, a determining factor here, it has to be large particles, things that are easy to see. Examples again, salad dressing. If you think about, I don't know, dirt, if you take large particles of dirt and water and you mix them together, and you could do this demonstration. If you take some dirt, just put it in water, shake it up, it'll stay a pretty homogeneous mixture, but if you let it sit for a little while, the dirt and the water are going to separate out. So examples of suspensions, those are good. Colloids. Colloids are medium-sized particles held within the solution, usually create a cloudy mixture, not something that you can see through. It's like opaque. You can see this here in the test tube here. That's referred to as turbidity. The amount of particles in the solution basically diminish the amount of light that is able to go through uninterrupted, so it's referred to as turbid. Very difficult to see individual particles. Usually they're too small for your naked eye to see, unlike what we saw in the previous slide with the zesty Italian dressing. The dressing molecules, the flavorings in there were large enough particles for you to see, whereas in a colloid, you don't see the individual particles. It's just all a homogeneous mixture. Something like blood. Blood might be a colloid. If you just take a vial of blood, it looks red all the way through. It's relatively turbid. It has all kinds of different particles and pieces suspended within the solution. If you put that through a centrifuge, you can get a colloid to come out of solution, and even though those particles are too small to see with your eye, you can isolate them and basically remove them from the rest of the solution. So that would be a good example of a colloid. The Tyndall effect means that light is scattered by colloidal particles. Like we talked about on the last slide, when we talk about the colloid, it has particles that will reflect light and not allow light to go through easily. Same type of thing if we're looking at in front of a train, that light that hits fog particles in a foggy morning, it hits those water particles and that light disperses. Rather than just being a straight beam straight ahead, you can see that as it leaves those lights, it kind of spreads itself out, and that's because it's being reflected off of those colloidal particles. So the Tyndall effect is the fact that with a colloid you do have reflection of light. It's not allowed to pass freely from one side to the other. So a good way of determining what a colloid is using the Tyndall effect. Electrolytes versus non-electrolytes. If I was there, I would do a demonstration for you, and I'll do it for you tomorrow. But Gatorade is something that people drink a lot of. It's good for athletes, things like that. The way Gatorade started, Gatorade was from University of Florida, where it's super warm, and athletes on the football team, while they were playing, they would sweat an incredible amount, and drinking water obviously was a huge thing, drinking enough water. The scientists at University of Florida developed this idea that if we create a solution that is more similar to the materials that are in your blood, so having salt concentration, having solutes, and mixing in with the water, that those solutions will be more readily absorbed into the bloodstream rather than just taking plain old water. So what they did is they basically made salt water with a tiny bit of orange flavoring, and that's what the players drank, and it was extremely salty and extremely distasteful, and it wasn't a pleasure to drink, and it would never have sold any bottles if it wasn't effective. Today, when we see Gatorade, it is absolutely loaded with sugar. It still has a lot of salt. That's when you see high in electrolytes. It's basically saying high in salt. There's a lot of salt content to those things, which makes them easy to absorb into your body. If we compare things like Gatorade and Powerade, Powerade has less electrolytes but has more sugar. Sugar is a non-electrolyte, and I'll show you the demonstration tomorrow. In order to be an electrolyte, it has to be an ionic compound. Ionic compounds make great electrolytes. Sugar is a covalently bonded molecule that doesn't break apart. It's not ionic, which would make it a non-ionic solution or a non-electrolyte. In order to be an electrolyte, it has to be an ionic solution or have ionic molecules dissolved or ionic particles dissolved within the solution. And I can show you this tomorrow. So a substance that dissolves in water and gives a solution that conducts electricity is an electrolyte. And I'll show you using a light bulb and a battery that if you put salt into water, you can pass current through that. That's the electrolyte characteristic. If you just take distilled water and put the same light bulb and electrodes in there, you're going to get no current going through because there's no way for the electricity to pass along those charged particles through that solution. It's just basically a mixture of water which doesn't by itself conduct any electricity. Now, as an example, if you had a perfectly clean, spotless bathtub that had no salt, no nothing in it, and you filled it with distilled water and you took a bath and your college roommate came in and threw a toaster oven in with you, theoretically, you would be okay, supposing that you didn't have any salt or any electrolytes on your skin that would be rinsed off into the water. Now, in no way am I condoning that you do this. That would be a very, very bad idea because there's no way you could ever get it that clean or your body that free of salts or electrolytes. So it's in theory, it would work, but in no way am I saying you should do that. So please don't go home and throw your toaster ovens on your brother and sister while they're in the bathtub. That would be a bad idea. But the idea of electrolyte is that you need that ionic compound in the water or in the solution in order to conduct electricity. And that kind of plays into what we'll see with Gatorade and what we'll see with Powerade as having high electrolytes or low electrolytes. It's basically the ability for current to make their way from one electrode to another. That's essentially what we're dealing with today. That's all I really wanted to cover. So if you have your textbook or can access the textbook online, what you can do with the rest of your time today is go over review questions, take some notes on diagrams that weren't covered here in the PowerPoint, and make sure that you're ready for discussion tomorrow. We'll go over your test, and we'll maybe even start a lab on sodium bicarbonate and hydrochloric acid reacting with one another to predict outcomes and concentrations and all that kind of stuff. So, sorry I couldn't be there today. It was kind of an unfortunate incident this morning, and if you care to see pictures, I'll show them to you tomorrow. Thank you for listening, and have a wonderful day, and we'll see you all tomorrow. Thanks.